Welcome to Mr. Source tutorial. On our previous video, under method of analysis, we considered mesh analysis. But in this video, we are going to be considering nodal analysis. Nodal is derived from the word node. A node is simply a point in a circuit where two or more electrical components are connected together. This analysis provides a general procedure for analyzing a circuit using the node voltages as circuit variable. Let's consider a simple problem like this as an example. The problem says, obtain the node voltages in the circuit below. Remember from what we defined as node before, this is our node. This is our node. First thing you have to do first is for you to select the reference node. The reference node is simply the common node in which all other nodes are connected to. As you can see, this node 1 has a link to this point. This node 2 has a link to this point. So our reference node can simply be taken, is always taken from the ground part solution. Now, our reference node V of ref or V0 is always equal to 0 volt. It's always equal to 0 volts. That is to say, the voltage at the reference node is always equal to 0. Next thing for us to do is for us to assign the voltages at the non-reference node. Remember, this is our node 1. This is our node 2. The voltage at this node, which is what we are looking for, we call it V1, as voltage at node 1. The voltage at this other node, we call it V2, that's voltage at node 2. After assigning the voltages, the node voltages, the next thing for us to do is for us to assign the current at each node respectively. This current is a 3 ampere current, This current is flowing toward this direction. If this current comes to this point, it will comes to this point, hit this node, split here and split here. We have to have that it's going to split like this and split like this. If this one now comes to this node, it will now hit in this node and split here and split here as well. So current at this point, you can call this I1, call this I2, call this I3, call this I4, call this your I5. Alright, the next step for us to do is for us to define each of the current at each node respectively. As you can see, let's start from current I1. As you can see, this I1 is simply this 3 ampere current that is coming from the source. So I1 is equal to 3 ampere. That's that. This is our I2. Now, it's worthy of note for it to know that in a nodal analysis, remember that Ohm's law says that current I is equals to V over R. But in nodal analysis, the voltage is here, simply the voltage difference from the higher potential to a lower potential. That is, if this current is flowing from this node down, it's going to be this V1 minus this one that is going, which is the lower part. If it's flowing this direction, it's going to be V1 minus V2, always to the higher minus lower. That is the note. So it means that and again, our reference voltage V of 0 is always equal to 0 volts. I2 can be given by higher is leaving v1 minus reference node, which is 0, divided by the resistance, which is 2 from Ohm's law. So again, it simply means that I2 is equals to v1 over 2. Right? The next one is current I3 is leaving v1 to v2. It's going to be I3 equals to v1 minus v2 divided by resistance, which is 6 ohm. That's very simple. This one is I4. I4 is equals to, is leaving v2 divided by the resistance is 7, right? Because this is leaving v2 minus v0, which is 0. That's why I didn't bother to write it again, like what we did here. The last one is I5. I5 is simply this 12 ampere current that's going out of the node. So I5 is automatically 12 ampere. Exactly. Right. Now the next thing is for us to apply KCL to each node respectively. Now applying KCL to node 1. But this is our node 1, right? Remember, KCL says that the algebraic sum of current going inside the node is equal to the current going out of the node. We have done this in our previous video. If you have forgotten, quickly go back and watch our previous video for more enlightenment. The KCL equation for node 1 can be given by this I1 is going in, I2 is going out, I3 is going out. Can be given by I1 equals to I2 plus I3, which our I1 here is equal to 3 ampere equals to, and our I2 here is equals to V1 over 2 plus our I3 here is equals to V1 minus V2 all over 6. This can also be written as 3 equals to 1 over 2 V1 plus V1 over 6 minus V2 over 6. Alright? So now, this is equals to 3 into 1 over 2 V1 will give us 0.5 V1. 1 over 6 V1 will give us 0.1667 V1. And 1 over 6 V2 give us minus 0.1667 V2. At this point, some person might wish to take the LCM of this and this and multiply. It will simply give it the same thing, but I think this one is the simplest way of solving this. So now you now see that you have V1 here, you have V1 here, summing it up together, this is going to give you 3 equals to 0.5 V1 plus 0.1667 V1 give you 0.667 V1 minus 0.1667 V2. Therefore, your KCL equation can be given by 0.667 V1 minus 0.1667 V2 equals to 3. Alright? Yes. This is simply the KCL equation for node 1. Now for node 2. Applying KCL to node 2. Remember, this is our node 2. Now, in our node 2, you can see that I3 is going in equals to I4 that is going out and I5 that is going out. So for node 2, the KCL can be given by I3 equals to I4 plus I5. plus I5 because they are going out. Now I3 is given by, from what we define here, I3 is given by like V1 minus V2, which is the value for I3, divided by 6, equals to I4 is given by V2 over 7 plus I5 is given by 12 ampere. Right? This is simply the same thing as saying V1 over 6 minus V2 over 6 equals to V2 over 7 plus 12. Some person might choose to take LCM and solve the same thing, but I think this is the simplest approach I've offered. So now, at this point now, you can collect like terms by taking this V2 to the left hand side. So you're going to have V1 over 6 minus V2 over 6. If this positive cross this sign, going to be negative, minus V2 over 7 equals to 12. So 1 over 6 is given by 0.1667 V1 minus 0.1667 V2 minus 1 over 7 is given by 0.1429 V2 equals to 12. You can see here we have V2 here, we have V2 here. Summing this thing together now, you are going to have this to be 0.1667 V1 minus this plus this will give us minus 0.3095 V2 equals to 12. This is KCL equation for node 2. Call this equation 2. This was your equation 1. Now recall, you now say recall equation 1 and 2. Equation 1 is given by this, which was our 0.667 V1 minus 0.1667 V2 equals 3. This was our equation 1. Equation 2 is given by 0.1667 V1 minus 0.3095 V2 equals to 12. This is our V2. Now solving simultaneously, you can use any method of simultaneous equation to solve it, but you're going to use calculator to make life pretty simple for us, which was what we did in one of our videos. So if you don't know how to use calculator to solve this simple simultaneous equation, you review our videos. To solve this with our calculator, to avoid waste of time, put the value for here 0.667 equals to minus 0.1667 equals to 3. 0.167 minus 0.3095 equals to 12. We're going to have that our V1 is given by minus 6 volts and our V2 is given by minus 42 volts, which is the value for the node voltages V1 and V2. In a normal condition, we always have current source, which is the normal procedure of analyzing the node voltage using KCL. But there are some conditions or some cases in which we have voltage sources that warrant in having a super node. So in our next video, We are going to be considering a nodal analysis problem which we have a voltage source instead of a current source, and precisely we are going to be studying how to solve a supernode network. Thank you very much for watching. Please, if you are new, subscribe to our channel for more educational videos. Thank you.